Okay, so we've got linear discriminant analysis. Or LDA. Okay, and what we do for this is, we have k categories, and we try to classify our data into the right category. And so what we say is that the probability that y is in category K, so given our x, so that we say x is equal to x, is equal, all right? We write pi sub k and f, not of x, f of k sub f sub k of x this is a L. Okay, and so what f sub k of x is equal to the probability of x given y is equal to k. So this is the density function of x for class K. Okay, so remember x, so just a reminder, K is categorical, or y is categorical in K categories, and x is numeric, right? So we are looking at the density function of x, and given a class K, p sub k, or pi sub k, this is the prior probability that an observation is in the K class. Okay, pi sub k is easy to estimate. So, you could supply it prior information, okay? But, pi sub k is easy to estimate. If you don't have priors. Just count how many are in each category. Just count how many observations are in each category. Okay, so, if you don't have any information, you just say something like, if half of your data comes from category 3, then your prior for category 3 is going to be 0.5. Okay, just something like that. So anyway, this is how we do it, and just practically speaking. Whoops, I should have saved this. Sorry. LDA, we'll try to find the dimension that produces the most differences between means. Okay, and so, let's say the true distribution of data. Let's say you have two categories. You've got one thing that looks like this, and then another thing that looks like this. Okay. So this is category 1, and this is category 2. So, let's say we're trying to classify who's male and who's female based on their height, or something silly like this, right? So what this would end up doing is we just say, oh, okay, over in this region, you have a higher probability of being male than female. So if you're over here, we're going to classify you as male. If you're over here, we're going to classify you as female. And probably our boundary is going to be right here. And what this will say is, or I don't know, maybe this is the female one, right? So this will be category 1. Category 2, this is our decision boundary. And so, it's going to get things wrong if there's a good amount of overlap. But, if you're making decisions based on a single variable, you've got to draw some kind of line and hope that that's the best spot. Excuse me, I got something in my throat here. Okay. When you've got more than one dimension, LDA does similar stuff. Okay. Except it's going to try to find so let's say you've got data points over here. And you've got data points over here. You got data points over here. So what LDA is going to do is it's going to look at this it's going to look at your, you got x1 and you got x2. It's going to try to, you know, split these apart, and I'm going to guess that it's going to probably do something like this to kind of draw your boundaries. And, you know, it's going to kind of find the mean of these points, probably something around here, and then something around here, and something around here, and it's going to just say, you know, based on something, you know, we're going to classify it this way, all right? So, you know, we can try this out with R, and we can see how well it performs. Okay. All right. So let's take a look at R. I'm gonna load up the data set MASS, and we're gonna load the iris data set. Are you guys familiar with the iris data set? It's like this very classic data set from like statistical history, okay? And so there's 3 species of irises, and we measured, or Fisher or Anderson, whoever talks about this. This is back in 1930s. Measured a bunch of 150 things, and they measured the sepal and the petal length and petal width. Do you guys know what sepals are? All right, I'll show you. It's just like parts of a flower. Okay. Here we go. This is not. No, of course. Whenever you. All right, so you've got the sepals and you got the petal. Oh, what is this? I don't think this is quite right. Everybody talks. Now, if I look up iris sepal, it's going to be just stupid. It's just everybody talking about the data set. Because it's so. It's now so entrenched that, like, all right, so it's, like, there's different parts of the flower. You've got the sepal, and then you've got the petal. So, well, I guess now I don't know which is which. Okay, so you got different parts of the flower. Let's look up what an iris is on Wikipedia. So one, oh, look at that, the iris flower data set. It has its own Wikipedia page. This is amazing. All right, well, yeah, so you can get this from Wikipedia, or it's already included in the data set. And then, there's 3 species of iris. This is the setosa, the versicolor, and the virginica, right? And I'm no expert on irises, but we can measure, the petals and the sepals, and try to create a classification system. Okay. All right. So let me see if I can just do pairs iris. All right. So this looks kind of crazy. All right. So we're just plotting sepal length versus sepal width, petal length versus all of these things. Let me just create some of these pairwise plots. So I'm just going to create a plot between sepal length and sepal width, and I'm going to color code them based on their species. Okay, so let me change PCH to 19. Just give it a little bit more color there. Okay. So based on this, can we differentiate How about that? Can you create good boundaries that will separate our data points? Okay, so that's somewhere along the way it looks like, okay, maybe we could use one of these things to kind of form some good boundaries here. Okay, this one seems pretty good, right? So it looks like we use these two pairs. So I'm going to use these two data points, or these two axes, to try to differentiate between the different species of flowers. Okay. So actually, let me go back and just we'll take off the filling in. Okay. So the way I'm going to do this is I'm just using the third and fourth columns, which will be petal length and petal width, and we're going to do a linear discriminant analysis with just these two variables. Okay. So you call it in R, very similar to linear model. You don't even have to write formula. You can just say perform LDA, where we are predicting species, or we're trying to explain species based on petal length and petal width, where our data is iris. Okay, so I hit enter, and it's done. So we can ask, what'd you do? All right, and so it gave prior probabilities of 0.33 for each group, and I think that's because there's 50 points in each group. And it said, okay, the group means for the Setosa is 1.462 and 0.246 for petal length and petal width. The group mean for versicolor is this, and the group mean for Virginica is this. Okay, so I can have it plot those data points. There's the three data points from our linear discriminant analysis result, which I've stored in R. I'm going to just say R $means, which is just this portion right here. And we can do this, and it says, okay, these are the means of those three groups. And so based on this, we can see, how good are you at making predictions. Okay, so all I'm going to do is I'm going to just feed back the exact same data and say, using your linear discriminant analysis model, make predictions. Okay, so I'm going to say, I'm going to give you basically the third and fourth columns from iris, which is just the petal length and petal width, and based on the information I give you, I want you to predict what class it's coming from. Okay, so we're going to just say make a prediction, and there you go. So here are the predictions. It's predicting Setosa, versicolor, and Virginica, which is pretty good, because in the data set itself, in Wikipedia, we can see that the data set is arranged by species also. And so we can create a table to see how well did our model make predictions against the truth thing. Okay, so we're going to just create a table of the actual species versus the predictions. Okay, so if the actual species was Setosa, it predicted Setosa all 50 times. If the actual species was versicolor, it predicted versicolor 48 times, but Virginica 2 times. Okay, and if the actual species was Virginica, it predicted Virginica 46 times and versicolor 4 times. So it's a pretty good model, right? Okay, so that's just using two variables. With linear discriminant analysis, you can have higher dimensional models as well. So here I'm just going to say predict species based on all of the data points. I'm just putting in a dot here. So we're going to create the full model here, and we're going to have it predict make predictions based on the 4 numeric columns. So same type of thing. So this one's we can't really graph it because I don't know how to graph 4-dimensional data in R. Okay, and we can create the predictions there. And so we see when we include all four variables, our predictions get a little bit better, but it still misclassifies maybe 3 of our data points here. Okay, so so that's linear discriminant analysis. I know I didn't really get into the theory too much. It's based on it tries to estimate the density, and a lot of times it places kind of like a normal density assumption upon our data, or at least a assumption of constant variance across the groups, and based on that, it creates predictions here. So linear discriminant analysis is good if the means of the groups give you a lot of information about which group or which category the data is in. It is not so good if the means are similar, and the thing that differentiates one group from another is something like the variance. So for example, let's say, okay, so I'll say LDA is good if you've got group 1 here and group 2 here. This is a good situation. Okay, LDA is bad if you've got something like this. Okay, because then in this case, both of them have kind of the same mean. A better model would probably do something like this. Will be category 2. This zone is category 2, and this right here would be category 1, or something like this, right? And here you would misclassify a lot because there's quite a bit of overlap. But LDA would not be able to differentiate this. LDA would try to draw one line and say, on this side is category 1 and on the other side is category 2. But if they have like the same mean, it's not gonna work. Okay, so here LDA is bad in this situation. So LDA is good when the class information is contained in the group means. Okay, bad in other situations. Yeah, I was debating how deep I wanted to get into linear discriminant analysis. I think I'll just keep it pretty light, and just like, this is kind of the overall big picture of what we're trying to do. Trying to create boundaries between data points based on a few variables, and R makes it very easy. You just say LDA and you kind of throw it in like a linear model. Okay, except the key difference here is that the variable that you're trying to predict is categorical, and then the other variables are numeric. Okay, so we'll keep it pretty light, and I guess that's all we'll cover for today. On Friday, we'll I'll talk about the final exam. I hope to have it all fleshed out by then, and that will be it. So see you guys in a few days.